Hello there. This is Juan David Roa, and this is a video about digital signal processing. In this video, I'm going to explain the basic concept of what a period is, both in continuous and um, discrete signals. Well, so let's start. Um, so before we start, I want to make the reflection on signal processing, which is basically the the way in which we can understand the world through um, mathematical descriptions of what a sensor could give us as an answer. Um, this is widely used in terms like physics, even aerospatial engineering, and in pretty much all the aspects of like human life that requires like transcription of the real world to a digital world. So uh, after this, let's start. So let's consider the signal. In fact, this p times t. It's not this one, but the main idea is this one. So we got a sinusoid signal that repeats itself each second, and that second describes our period. So our period is equal to time, or the cycles in that time. As we have described here, one single like phenomenon that occurs or has the same behavior uh, in a period of time, because these are these are periodic signals, is described as a period. So in this case, we have this like maximum height in a period of 1 second. So that's period. We got also frequency, which could be both like our normal frequency or angular frequency. So angular describes like the form in which it repeats in a kind of like radial motion. So that's why we got 2p. And these are pretty much the formulas. But what it means, the frequency describes the times uh, that it happens, that a cycle happens in time. So in 1 second, this phenomenon occurs one time. So this is why both the frequency and the period are the same in this case. If we move on to this one here, which is going to raise that, which is not correct at all, we can see that it has doubled. I mean, we have seen the same effect 2 times in 1 second. So in this case, the frequency will increase while the period will decrease. Why? Because we don't need to wait 1 second for the same phenomenon to occur, but actually we just need to wait half a second. Half a second. So this is why the period decreases and the frequency increases. They're inversely proportional to each other. And we got this one right here. So we are waiting more time because this is probably going to repeat in 2 seconds, whereas we just have half the repetition in 1 second. So the period increases and the frequency decreases. All right, so we also have this concept, which is basically what will happen if this is constant. Well, the frequency is 0 because it's not repeating a phenomenon. We have the same answer, and this is 0 hertz. This is the measure of frequency. All right, so let's move on with discrete signals. This is an example of a discrete signal. So we got like a particular point in time and nothing else. Like just whole numbers. This could be 1, this could be 2, this could be 3, 4, 5, 6. But we cannot have like 1.8. This is not possible in discrete. You need to have the same frequency, the same like distance between one and each other. All right, so we have like this they're new uh and this is normalized frequency. In this case, as we can see, this has the same value, so the value is 0, but it acts a bit different. So for example, we produce a sinusoidal signal, and as we can see, the time for reach 8, I mean the time that it requires to reach the same thing is it's longer than just 1, so it decreases. But we have actually 2 ways of saying it. This is another example, and I explain what I just said later on. So in this another example, we can see that the time decreases. So the period of, I mean, the value of this normalized frequency increases, but cannot be larger than 1/2, because otherwise we couldn't see like this repeating once again. This is like the relationship between uh, what it would be a continuous and a discrete signal. So as we can see, the normalized frequency of the continuous one, say, so this one could be summarized into this formula, kind of. So we see it repeats every 8 seconds. All right, so let's continue with actually the period, which is what matters, and what I'm going to explain with our MATLAB program. So we have our continuous signal with this formula right here that I already explained. But in discrete, we have this value n related to the angular frequency here. So for discrete, we have a relationship of n over m. And well, this relationship explains why every discrete signal must have be multiplying time, or well, n. Because otherwise it couldn't be like periodic. So to summarize everything that I just said, I'll explain this with this formula right here. So this is an the Euler identity, which basically relates the expression of a imaginary number with sinusoidal expression. I explained this later on with the MATLAB program. So this is the magnitude that multiplies both functions, or in this case, signals. And we got our angular frequency. So to calculate the period, we will realize that they work quite differently. In this case, they are the same, but actually they are different. So, for example, in this case, if we use this formula to calculate the period in a continuous signal, we get 6. But for discrete, we actually get 6 too, only because they are pretty much the same. But this is not always the case. All right, so I'll show you another example. So let's consider we got an angular frequency of 3 pi divided by 4. So in continuous, and discrete, they will work quite differently. So let's go with continuous first. So we know that the period is equal to 2 pi divided by the angular frequency, which in this case is 3 pi divided by 4. These two cancel out, and this one multiplies this one. So this will be 8 over 3, which will be approximately to that 67. And if we go to the discrete signal, it will work in this way. And it's actually the period, where is m is like a relationship. So we got 2p, and we got the angular frequency, which is in this case 3 pi divided by 4. So these two cancel out. This one multiplies this one. So n equals 8. And m equals 3. So period, this case, is 8 for the discrete signal, which is not the same as the continuous one. With this example, we can understand that they were quite different. All right, so let's move on with the MATLAB app. Hello there. So the first thing in this section of the video, we are going to use our MATLAB app. I'm going to explain how to download it and, well, the properties and what we can do with it. So the first of all, we have to have MATLAB installed. So we open MATLAB. All right. So the first thing that we have to do is like go to the section of apps, click on it, and once we like download the archive, we have to locate the archive in a special like folder or section. So what you have to do is basically go to install app and look for it. In my case, I developed the project, which is the app here. So right here, this is the whole app downloader. So we open it and we install it. Once it's installed, all we have to do is go click this little corner here in the app section too. I'll look for it. So we see here I have two apps. In this case, I'm going to use this one. We can actually see the properties of it, as you can see. So while what we have to do is basically just click on it, and this is the first thing that opens up. So I made this app thinking about what the teacher asked for, but actually I did a little bit more. So we got here for the Euler identity, which I already explained. So it divides into cosine and sine, and uh, as we can see, we can play with it in magnitude. For example, we can introduce 4. We say plot, and we can see that the magnitude has increased. So it's not only here in the real part, but actually here too. And as you can see, for the real part is the cosine, for the imaginary part is sine. And it's like the spring. This is like the spring that forms. We can actually play a little bit with it. We can rotate it. Let's leave it this way. We can actually see the periods. The teacher said that we have to just have 2, but actually you can see more. So this is how this function forms. We can actually play with the angular frequency too, which we will see the change in time here. So for example, let's introduce 6, no, 10 to look it better. So as you can see, the times that like the time that it requires to make a single period uh, decreases, and the time that the repetitions per second increases. So you can see that it repeats itself in 1 second, and well, the other properties. We have the calculated period here too. The function is just like this one. It's not multiplied by p, so this is probably why we don't get like a more precise thing, but pretty much plays with the angle. And we have a comparison between continuous and discrete signals. So here, this is what will be the, the angular frequency. It's numerator and denominator for red. And we'll see that we actually have like some other stuff like here, like magnitude and the m value that I actually talked about before this. So if we have these normal values, we can see that the the calculated period in both in discrete and continuous is going to be 2. So let's change it to the value that I calculate here. So let's say 3/4 plot. So as we can see, the teacher actually said we have to show 3 periods. So as we can see, this is 1, this is 2, and this is 3. This is how they work in Discrete. They don't work like continuous that we have to count from the second repetition, just the first one. So as we can see, the green lines represent the discrete periods, and the others just the repetitions. So the magnitude is still 1, as we can see 1, and the calculated period, in this case for the continuous one, is going to be to that 6, which is 8 divided by 3. So we can see it reaches 8 and it finishes because we are just showing 3 periods. But as we can see, the 3 periods are larger for the discrete signal. All right, so this is pretty much all of it. I hope you enjoy it, and actually learn a little bit of uh, signal processing, which is a quite useful area, especially if you are in engineering. So not only for electrical engineers, but actually for mechanical, mechatronical, and even uh, aeronautical engineers, which is a pretty useful topic we want to talk about, like um, what we can see in a digital way. So thanks for watching. Have a good day.